In today's fast paced world, unmanned aerial systems or drones are becoming increasingly integral in various applications, from aerial photography to search and rescue missions. But what keeps these drones stable and on course? In this video, we'll delve into the intricacies of a cascade control system, a sophisticated approach to stabilize and control the movement. This diagram illustrates hierarchical structure of a cascade control systems where each level of control contributes to achieving stable and precise control of a drone. Outer loop or a horizontal control controls the tilt angle phi of the quadcopter in the x plane to achieve the desired horizontal movement. The position control, which is the outer loop, controls the position of the quadrupter in the y plane. It generates set points for the inner loops. The inner loop or the attitude control is responsible for adjusting the drone's orientation, specifically its roll angle phi. Within this loop, the attitude controller employs a PID algorithm to minimize the error between the desired and actual roll angles measured by the onboard sensors. Now we will see how are thrusts calculated. To calculate thrust for a drone first, the drone's mass m and the gravitational acceleration g are considered. The desired roll angle phi c for a horizontal adjustment and the total thrust required for vertical adjustment are determined based on these errors. Finally, the calculated thrusts are converted into throttle settings for the drone motors, ensuring precise control and maneuverability. Tuning the system. We set PID controllers for all the gains as 0. We began our tuning process by focusing on the vertical control. We gradually increased the proportional gain while observing drone's behavior in response to the changes in attitude. As we increased KP, we noticed the system's response of the drone. Once we found a suitable KP value, we introduced derivative gain KD to improve the response of the vertical control. By increasing KD, we aim to dampen oscillations and improve the stability of the attitude control, especially during rapid attitude changes. Additionally, we introduced the gain KI to address steady state errors in attitude control. To optimize the drone's performance, we conducted tuning on both horizontal and attitude controllers. For a horizontal controller akin to the vertical one, we fine-tuned the proportional derivative integral gains Kp, Kd, and Ki. Gradually increasing the derivative gain Kd enhance the responsiveness of the horizontal control, minimizing overshoot during rapid position changes. Moreover, adjustments to the integral gain Ki were made to mitigate any persistent errors in sustaining the desired horizontal position over time. Iteration and fine tuning. Vertical controller fine tuning. We closely monitored drone's response to altitude changes over time and recorded the error difference between the altitude and the actual altitude at each time step. Using this data, we plotted a graph of error versus time off to visualize how the vertical controller performed under different flight conditions. Based on the error versus time graph, we identified areas where the controller exhibited suboptimal performance, such as excessive oscillations or slow response to altitude. Similarly, we fine-tune the horizontal controller. We monitor drone's position error, the difference between desired position and actual position over time, and plotted a graph of error versus time for a horizontal control. By analyzing this graph, we identified any issues such as overshoot oscillation or sluggish response to position changes. We adjusted PD, derivative, and integral gains to needed to improve the controller's performance. The consolidated graphs represent the error versus time position for x, for y, and the phi position. In summary, the cascade control system orchestrates a symphony of control loops working in harmony to stabilize and maneuver the quadrotor drone with remarkable precision. Thank you.